My name is Sudhir Vemula and I work as a design verification engineer at Revos. Today I am going to present a topic. I think this is popularly there from last Gen 2, Gen 3 also, and why it's very important in today's modern architecture, and I think it's 8 years. Address translation services and its relation with PRS also, like page request services. So we will talk about mostly why ATS are important in this today's modern architecture, and it's mostly I am DV engineer, so I will talk more on how we need to test these features, these capabilities, and some of the use cases and some of the other cases. My focus will be more on how to generate test cases and other cases in my verification strategy. Some techniques, how to generate stimulus effectively, and the checker mechanisms, everything we will talk about that. Okay, and this disclaimer, please note that all these opinions are mine only and not any official PCI SIG. This is quick overview of today's section, and I will start with what is the introduction of PCIe, ATS and PRS and its importance, and it's actually invalidation flow we have, and what is the use of this invalidation flow. Then I will shift my focus to verification, DV. Mostly I will start with key challenges and technical challenges, and to overcome these challenges, what verification strategy I followed is a common strategy, but with simple change, how I achieved to generate so many corner cases, and in block level only how I generated all the stress cases. We will go to that one. I think I use the UVM test bench, and we have UVM callbacks and randomization already available in UVM, and how I use that effectively in my test bench. And some of the test scenarios I will explain with my setup, and how I reuse that in system level verification and stress testing also. Okay, some fault cases also we will verify. I will explain, and why it is important in ATS, and I will wrap up with some takeaways. Just start with a little introduction of ATS and PRS, and I think is there from long time, but I will give quick overview of this one. And I think in PCIe architecture, like in the traditional PCIe systems, if you want to the device, it's want to access any memory location, then it needs to talk to CPU or like IOMMU to get the latest, means to get the it need to map the virtual address to physical address. For that, it need to talk to CPU or IOMMU. This ATS capability, it solves that problem, because it will cache the translations locally inside the cache. So this caching mechanism helps to use that physical address directly without the use of CPU and IOMMU. So this mechanism, I think a little introduction about the diagram, like if you see the PCI device, we have PCI device, and it is asking it is asking for it asking for actually the physical address. So it will ask in ATS request with untranslated address, and the root complex coordinates with the TA agent, and the TA tells that actually TA is connected with ATPT, and ATPT has all the memory mappings. So the above TA and ATPT is like a software version you can think, and we will get the untranslated address to address translated mappings. We will get that one, and that information is sent to device in ATS completion. So once ATS completion got that all the information, the ATS the device will cache that information. So from that time onwards, if device want to use that same the other like physical address, then it can use that memory mapping only. So it's like we are caching the system level memory mappings internally in the PCI device. It's like we are offloading all these translations inside the device. So it minimizes the I/O performance and it minimizes the latency. The main thing is it reduces the CPU interaction. Okay, I think if you see just a simple thing, the TR request like the simple ATS request looks like memory read only. I think there we have AT field. If you set that AT field to 01 like translation request, then it will convert like translation request, ATS request, and here I think all other fields are similar like relax ordering tags, everything is similar because that is memory read request. Okay, and this feature is more useful because if the device want to have only read access, so then we can use this no write flag to 1. So it is like game changer, because it's not game changer, it's like very important feature because the memory mappings, no need to make the TA, no need to make that page to that TA or something, just it will give the read access for that. Okay, and the translation completion, it is similar like CPLD only. The CPLD with DW is always 2 actually. In the 2 data words, it will embed all the information like the translated address and its memory attribute values like access rules and the attributes of the memory, everything it will embed in that information. So this information our device will cache. I think there are certain rules are there, like there are certain things are there. We need to consider all these things in verification plan because for one AT request, maybe TA can send 2 or more AT completions also with different memory regions. Even these regions can come in out of order. So here only the simple complexity is adding. Yeah. Okay, until now we just talk about what is ATS, and if ATS is not available, okay, if you see here, the device asks TA agent for the ATS request, but TA is not ready with actual physical address because it don't, the page is used by some other VA devices, or maybe that page is not available. Then that time it will send fault information. If it send fault, then device may request after some time the same information, or it can if PRI capability is enabled. Say I am talking about PRI now because ATS and PRI is interconnected. So if PRI capability is enabled in the device, then it will give the page request. The device will send the page request with that untranslated address, and it will forget. It will wait for the response. Then the device can continue to the next DMA transfer. So until the TA ready with that page, then it will respond with that. It will respond that okay, success. Now that page is available. Then the DMA, actually PCIe DMA, which is giving this address translations, everything, it is responsible. So the DMA software again request for TA request like translation request, and again it asks for the new physical address. So it's like we are not waiting until to get the physical address. We are going to next request, and we are making our DMA without stopping our internal FSM. We are continuing that work, and we are just waiting for page response. If page response we got, means then we are continuing the previous transaction, the previous DMA instruction. Okay, so this is PRA capability. Now if you see ATS and PRS, if you enable both the capabilities, then it's like we will see lot of good performance, because no need, if page is not available also, we can continue and we can use this PRA capability. Okay, it makes dynamically we can access memory pages, and it minimizes the latency and improve the I/O performance. Okay, because the memory regions now in the currently the virtualized environments and the cloud systems are there, and so many SVM like shared VMs are there, and CXL.cache devices are there. So everyone is using the same memory sometimes. That's why this capability is more important in modern architecture.
So once the page response is received, we have to send the address translation request again.
after we got the response, then again the translation request we need to send. Here's some small mistake here. It's like we need to send again a translation request. It's not the translator request.
So this thing will happen during link-up time?
No, it's during traffic going. This during DMA command processing time. After link up, we will enable this capability, like MSA, all other things. Yeah, I think this PRA request, if you go to schematics of the PRA is message, and that message, the PRA is message, and the coordination for PRA response and request is with PRG group, and to reduce the overhead, they have the encoding mechanism like for this 32 PRA requests, the RC can send one PRA response. So like the overhead in this protocol, this capability is already reducing the overhead. So we can, this improves the performance a little bit. And this PRA stop marker, okay, whenever there are events like FLR and DEVO, I think low power states, all these states, the PRA stop marker, they have the stop marker message format also to coordinate whenever FLR happens. And we need to remember this PRA is PF capability, not VF capability. So currently we can support 32 outstanding page requests in RC.
So this one is supposed for FIT also, and FIT mode Gen 6.
Yes, it's Gen 6 and Gen 4. Yeah, it supports for Gen 6 also.
So at a time the packet can send only, like if till Gen 5 it can be like 4096 bytes at a time can, but in Gen 6 onwards it has a FIT mode.
Yeah, and this capability, it's work like it's page. Like page means default page size. It will work like 4K. Yeah, and we can increase the 4K size to a lot of big sizes also by the capability setting. Yeah, but currently 4K aligned transfers pages we are talking here. Yeah, I think I just told what are the main importance of PRA and ATS combination. So it's like it reduces latency because it cached internally the address translations and improved IO performance. The protocol itself have all the like thinking about like how overhead can be reduced. So that's why even end-to-end performance also improved because now virtual to physical mappings we are doing internally in the device itself. And it's scalable to, it's not only for simple device to device not communication, P2P, not like that. We can scale this one to large memory regions where there are SRIOV devices and outside other devices like now CXL.cache is coming. So it's like other type of protocol. So, and a lot of cache devices are connected in our system. So this protocol itself works effectively. And this, I think, as use case I already told that, CXL cache and SVM, like shared virtual memory devices, everything. All this type of devices, this capability helps to reduce the low latency access and memory coherency problems also it will solve. Yeah, until now we talked about ATS and PRS because I'm roughing about, I want to go to design verification flow, that's why I'm rushing this capability. It's like introduction is, we have from this capability from Gen 3, I think. I think this invalidation means why this is one more message in this capability mostly we are using because this ATPT like address translations which are there in TA agent, these will change always because the TA, it has associated software, correct? The software, whenever because these memory regions are not static. So whenever the page, it needs more memory, for other devices asking for more memory, then the memory mappings changes always. So that time, the local cache which the devices has, it will become obsolete, correct? So it will be no use. So it will become like stale addresses. So to clean up that one, this ATS invalidation request we will send. So in this invalidation request, actually TA will trigger this invalidation and RC will send this invalidation to the corresponding device. So this invalidation request looks like, I think here I told the schematics how does request look like. It has I tag for the coordination between request and completion. So invalidation request will be there, it will coordinate it with invalidation completion coming from device. And pass ID, because these memory regions are not only, it will support pass ID also, this invalidations. We will go about this pass IDs later. And yeah, I think this invalidation supports not only 4K page size, we have the mapping like S-bit mapping internally to tell not only 4K, it's complete like 5G, 6G, at how much memory region you want to clean. We have the capability inside this invalidation request. And the payload, usually we will put payload like untranslated address to clear that memory. Yeah, I think some of these other schematics like completion count, I tag vector, all these are like important in that vector, like invalidation request. And the important point we need to remember, and as the verification point, it's very important to understand that these invalidations can come dynamically when already some the AT requests are going on, like DMA already triggered, or it is waiting to trigger the next AT request inside the DMA. So during that time also this invalidation can come. So that's why we have some conditions to follow. When invalid device see this invalidation ATS invalidation request, then it don't send any new TLPs with the stale translations. It will wait for receiving all address completions and complete discard the stale translation completions and send all the posted already existed, we already kept in the queue, and that posted TLPs it will send. After doing all these works, then only it will respond with translation, completion, invalidation completion. So TA understand that before this completion it is using old address, after this completion it is using new address. Or it is cleared. Again it will ask for new TR request. Yeah, these.
If the device does not respond to the completion of invalidation request, then the IOMMU is in hold state, not able to allocate memory to other softwares, right? So it may cause indefinite delay. What happens to the device?
Yeah, it's like timeout mechanism we have, correct? Usually this protocol telling that we need to respond for this request. If it dropped, then again RC will send like TA send one more invalidation request because completion not came within the time period. So this overhead need, that's why here the coordination should be there. Our device need to capable correctly about this invalidation. That's why verification is very important here. And these are the common checkers we need to do in our invalidation sequence, because invalidation is the complex one here. So that's why when it will be dropped and when we need to send UR response. And I think if any device is sending ATS request, then always it need to snoop the existing translation. So all these important points we need to consider while developing our scoreboard or reference model also. So that's why the perfect verification of ATS, PRS, and invalidation helps so much. It helps so much, and the I/O performance also improves very much. Yeah. Now I think the basic introduction I have given for about ATS and PRS and invalidation. Now we will see what type of complex scenarios we are getting with these capabilities. Yeah, and we already told the challenges. I think the DV challenges in this capability is like the consistency, like we need to check virtual to physical mappings happening correctly or not. Our reference model need to have two snapshots, like inside the device cache and inside the ATPT. So we need to check both, and when invalidation completion came, and which physical address we need to use, which absolute address we need to ignore. All these checks we need to put in our reference model to verify this capability effectively. And the correctness, like the data accuracy also is important. Address translation accuracy, everything is very important here in verification point of view. And coherency, because now if you have one device and one TA, it is okay. If you have multiple devices and multiple VFs and multiple like PFs, then the coherency because the device can store this memory regions with respect to requester ID, with respect to VF ID also. So I will go to that one. So that's why cache coherency is important, and security. And internally, this protocol itself has access rules, like this device, it is asking read-write permission it has or not. If it don't have read-write permission for the device, the protocol itself, the TA itself send the fault information for that request. So inbuilt this capability has the security information and scalability, and we can use this for different pass IDs and different devices also, like multiple devices. Okay, these are the key challenges, but during our verification, what are the technical challenges we face? Because that, of course, cache means there are so much complexity involved in verification. So even these three capabilities are making race conditions. So that also we need to verify. And yeah, mostly invalidate race condition is the one of the important thing to verify. And fault recovery. So this capability is per PF and per VF separately. So whenever any fault came for VF, one VF or one PF, then the system should not fail actually. It should recover automatically, and the translation should work as expected. So fault recovery is very important scenarios we have to verify. And yeah, randomized test scenarios. Currently we have UVM methodology. In UVM methodology, create random packets like responses, and it will send. But here the connection is like random response itself not sufficient, because ATS and PRS and invalidations are connected now. So these three we need to verify at the same time. So to verify that one, to make testing, so I will explain the next slides how I make that one. Yeah, I think my verification strategy, like I developed the UVM test bench only, and I use the existing vendors for the Denali, Cadence, Denali VIPs for integrating to mimic that RC and EP agent, and it has inbuilt checkers for all our protocol rules, everything. And I think the reference model, I prefer the instead of writing scoreboard plus reference model C++ I use. So it makes that we can portable for all other methodologies. And yeah, I think that is a small introduction about my test bench. And the first block level test bench, I used only one device and one RC, and one RC, and the same test setup I reused for system level with multiple devices, with assigning multiple pass IDs for each device. I reused that same test bench. And yeah, I think my test cases are like coverage driven. So each test plan has cover points linked to that, and that to cover that cover points 100%, I have written constraints in a way that how many transfers I need to send in one test case. So I will go to that one. How easily I verify that one, I will tell you. And yes, test fault and system level, I have the introduced fault cases. I think some of the fault cases I will explain at the end. Yeah, and block level test bench, I think this is the little introduction about block level and how our block level first minimum setup will be there, and we need to integrate RCR, EP, agent in our test bench, and I think we need to make sure the capabilities are equal in Denali VIP or any VIP agent, and our DUT should be same. During enumeration, usually we will get the values synchronized between both, but the important capabilities I mentioned here, because these are like these makes the traffic change always. So one is like a page align request. We can always, it will be page align request if you want to send, but we have the capability to get address on non-page align request also, and invalid, global invalid, because inside our cache with respect to pass IDs, the memory regions will be stored. If we want to clean all the pass IDs, then we can use this global invalidate feature. And it's not a read-only bit, it's a relaxed order bit. I typo mistake here. And yeah, if you want to enable relaxed order, we can enable this attribute, and device no need to use the same thing like okay, we got a request with RO set, no need to respond with RO set only. So that things we need to consider. and memory attributes if you want to enable or not, and pass ID we need to enable because pass IDs are linked with ATS and PRS and invalidation. And outstanding page request, I think device and RC will communicate how many pages it can store and how many pages it can assign. So this it will use in the capability registers. Once all these capabilities are set internally between both, then we will enable ATS and PRS. So this is our configuration part inside our test bench. Now we have to mimic in our block level test bench. We need to mimic that TA agent and memory regions in ATPT region. So to mimic that one, I think first we need to understand how this ATPT regions looks like. If you see the regions, I think this is one of the region snapshot I mentioned here. The region should have untranslated and translated and size of that memory region it need to be mapped, and the access permissions for that memory range and pass ID. So it's look like if you see the complexity involved for developing this memory region itself, if in the ATPT, it is in ATPT table. So with respect to pass ID, the region will have different meaning. With respect to pass ID and privilege mode, we have different meaning, means different translation region we can declare that. Okay. We made somehow, we cleaned that, we randomized and we came to some address ranges, but still it's sufficient to verify? No, because if this region, we don't have this region inside our device cache, then only PRA capability will come. In our test case, how we can tell that how many PRA requests we got it and how much randomization we need to do for the PRA response. So all these controlled in the test bench by using weighted randomization technique. So this, because randomization is so much here. So, but if you leave that one like that, we need to send lot of packets to achieve all this functionality. So corner case scenarios you need to hit means we need to set so many packets. That's why I use callbacks. In the callbacks, I change the behavior of the packet. So, and changing the behavior, like we can change it for all the packets? No, we need to dynamically change for some packets, and some packets should be good packets, some will be negative packets. So to make that clean, I think I use a weighted randomization. So maybe in the next slide, this is a simple code I have written in my config file. If you see, I declared one variable like trigger invalidation with 100 count and ATS error response, PRA response delay. So means this code, what I am telling is, I am making one vector with 100 bits initially set to 0. In the test case, maybe for example, I am telling that ATS error response weight is 75, means out of 100 ATS requests, 75 should be no permissions. So if you see in this 100 bits, 75 bits I am setting to 1. So randomly I will shuffle that one. So means that out of this 100 bits, 75 randomly set 1 actually. So it's randomly set 1 means, so whenever this for that ATS request invalidation is triggered with 1, then I will send the stimulus. I will send the sequence. So it's like look like in one test case we are controlling how many percentage of ATS invalidations we need to send. It's not like directly randomly send for so many packets, so many. We can use distribution also, but the distribution will help for the only certain number of packets. Like if you leave the test case with 1000 packets, but I want 100 packets only invalidation request. Why we want like that? Because if invalidation is not, invalidation access permissions are not coming correctly, then only PRA will come. So that's why we need correlation between these three capabilities. So to correlate that one, even I will explain how correlation constraints I have written in the next slides. Okay, if you see this example with these two settings, I am getting the functionality like okay, in the one test case, I am sending ATS request 100 ATS request. Then 75 requests I don't have permissions, no read-write permissions, and it's like it is mimicking that TA is responding with fault for that 75 packets. And for that 75 packets, 100% I kept for response delay because DUT, like not DUT means I am telling EP here. EP responded with page request. For that request, I am sending response, delaying that response. Internally we have the sequences, and the sequences we can delay with packet delay or interpacket IPG delays. We have, because sequences available already existing in our VIPs, UVCs, but how we need to use that one, how many packets we want to control the delay. So all these things I am controlling with these runtime arguments. Yeah, I think if you see, for every 100 packets, I am reshuffling here. So the first time I got with some packets, next time I will get randomly with another packets the same behavior. Yeah, I think one of these simple scenario I explained here, the last error, I think ATS error response 75 and PRA response delay means, so out of 100 packets, 75 packets I am getting, means in this test case, if you send ATS 100 packets, then 75 page requests also I am getting for that in the test case, and the responses are coming out of order because the response delay I am randomizing here. The UVM randomization is already there, but I am controlling how many packets I need to send in this test case with PRI and invalidations and with this with other error responses. And not only these simple 2-3 weightages, I can use for so many weightages. See, in our test case CA, how many responses I need to respond with CA response, how many I need to respond with UR. So all these things I can control in my with config file only. Once this standalone like runtime arguments are working, then I can use one config file to randomize the connection between all the packets, like how many CA return I need to send in out of one test case, how many UR I need to send in one test case. So this makes our debugging also make easy. And see, I think I got one of the requirement like one system requirement like this. So I can write one constraint file with dependencies for all these weightages. So these weightages tells me to achieve this system level functionality. So if you see this constraint simulates a congested PRA response path often triggered by ATS failure, leading to more aggressive invalidation sequences to reclaim ATC consistency. So means that if you see the simple meaning, we need to test more invalidation sequences we need to test, and the PRA responses we need to send more PRA responses in the same test case. So for that I used connection between these weightages to get to mimic this feature, system level feature. So this constraint I can use in system level also if there are multiple devices, and it's simply like we are coming like one step to one step. In block level we are creating the setup, and then we are using the same setup in system level by changing the weightages automatically. In the test case it will automatically randomize in each time these constraints. Yeah, and we will talk about some of the corner cases, some of the important cases where we find more bugs in these capabilities. And yeah, you can see how the basic test config I have written here. These configs helped me to verify all the corner scenarios in the first step only. Yeah, and some of the scenarios we will talk here. And I think one of the scenario I am telling that invalidation matching outstanding ATS translation request. Now complexity of test cases is more because we want to send ATS request. ATS requests are going on from the device, but during that time we want to clean the cache. So to clean up the cache, so we need to send invalidation request with the same address. So to match this scenario, test plan scenario, I need to control from the config file of these weightages. Like I am increasing the invalidation weightages, and I am telling that when ATS requests are this much count, okay, in this test case I have ATS request as 25, 30, 50. So then invalidations I am putting like 100%, means for every ATS request I need to get invalidation with the same address. Then here it indirectly helps to verify if I put invalidation timeouts also in the same test case, means some invalidations I need to do timeouts. So like that, I am increasing the complexity of the same test case by just controlling these control arguments. Currently, we are using only these control arguments, but the percentage weightage distribution we are not giving anywhere. So if you give the distribution weightage also, then if you write constraints between these value control fields, then we will achieve this all type of complex scenarios in the first step only. So that's why. And maybe if you see, there are some scenarios where I find more useful to verify with this methodology. If you see invalidations count is greater than Q depth, like here is helped me to change Q depth value with respect to constraint and give the weightage of invalidations with respect to Q depth value. So I have written in like in main test config, I have written the constraints to like whenever we have depth 8, then if invalidations are increased more, then it is more than Q depth we define. So that time we will have back pressure from the device. Because at the first step, if you verify these type of features, then we never know where the problem is coming. So then if you test is failing, then we will see the test config, okay, how many transfers we sent in this test case, and then we will come up with the debug strategy. Yeah, auto enabling, I think disabling ATS means there are some scenarios where ATS and PRA will be disabled automatically. So one of the scenario I can tell that if PRA receives malformed packet, internally the PRA capability will be disabled automatically. So FLR comes, it will disable. So during that time also, the outstanding transfers, how we are handling internally. So to verify this one, we need to enable this FLR, means we need to, there is one test scenario like we need to have 20 outstanding currently. During that time, FLR need to be released. So that time this constraints helps, okay, PRA response should be this much and PRA error response should be this much, and FLR initiate after 50 packet or 20 packet like that. So then we will achieve this functionality very easily. And the multiple translations, yeah, I think we have this feature like instead of single ATS, multiple ATSs also we can release, and the batch completions, like all these scenarios. I think some scenarios I told about with control fields. And this connection, I think we already talked about the connection. So if you see the weightage scaling, like I use a scaling mechanism also, like initially I started because every test case don't want to run 100, 200, 1000 packets. So instead of 100 weightage, I use a scaling factor like 100 into 0.1. Every 10 packets, I'm injecting some errors. If you go to the same setup, if you want to use for more packets, like 1000 packets, the scaling factor we can increase to 10 like that. So we can use the same setup in system level with more number of test cases and the same controllability. Yeah, and the checkers, and I think the important things we need to verify in the checkers, like the basic UVC checker will tell that it is following all the protocol rules or not, but our reference model need to be validate the ATS transaction ordering and the permission checks and compliances across these 3 flows. Okay, I think I use C++ because we can use the same setup for simulation, emulation, or any other environments also. Even system level also, it's easy to change. And yeah, this technique, usually this methodology, this method what I followed is helping me to detect bugs early in cross environment, in our block level itself, and I can use the same setup in system level. Cover points, to writing cover points, maybe if you want to see initially, so how many constraints, how many constraints are hit, it will at least tell that how many scenarios we already hit. Even we can write cover points to understand really that scenarios came in the monitor or not. So I think for time factor, I use constraints to cover all complex scenarios are hit or not. I think one of the complex scenario I can tell. So invalidation sent when ATS, when page response also sent. Page response and invalidation sent at the same time. Means device received the page response and again it is doing translation request for the same address. During that time already invalidation is existed. So these type of complex scenarios and cross coverage also we need to get for that complex scenarios. So that's why across ATS invalidation, across PRI invalidation, we need to write cover points for that to cover all the scenarios. I think already for all three scenarios also sometimes cover points is required because pass ID with respect to pass ID in values, the memory regions will change. So I think all these things we need to written in cover points to validate all type of corner scenarios are covered or not. I think currently we can use the same config file, but if you want to spend good time, then we need to use the monitor. We need to copy the same setup in the monitor also. So it's like monitor means I am telling that at input we are altering the packet, at the output the packet altered or not, and what is the monitor responses we got from the UVC. We need to create the same setup for, instead of trigger invalidation, we need to check monitor invalidation. So that monitor invalidation we can use for the cover points. Yeah, I think there are some system level scenarios. I can tell that end-to-end behavior is very important to verify in these three capabilities, because until now we discussed about one device and one RC like that. If you want to have more devices, more pass IDs, and like it's mimicking like virtual VMs, so many VMs are there. So that time this system level verification comes in picture, and we can use the same constraints by putting multi-dimensional array by using one dimension as like requester ID, like device ID. So then we can increase the same setup for multiple devices. And testing also, like for race to mimic that race condition, like yes, if you can see this pass ID runs and the coherency, ordering consistency with high volume DMA pages. So testing automatically we are covering with this setup, which because the same setup like with different pass ID numbers, we are increasing the complexity of these constraints, or we can put always 100% for all the scenarios, and even UR/CR cases and FLR cases we can control inside our same test case, and no need to compile every time if you use runtime arguments also. Yeah, I think fault injections, until now we talked about the scenarios about normal cases, but fault cases are existed, like if you drop some of the translation responses, and if you drop some of the if you change the order of this translation response, or invalidate completion response, or if you delay the response. So how the system will recover all these type of errors? And we are sending invalidation request with different pass IDs which are not existed in that memory region of that device. So that time how DUT is responding, because it no need to rush up for that request, correct, because that reason is not existed. So the ordering we need to see that time, and invalid mappings, how it is coming. Only the goal is one thing: whenever any fault comes also, the system should not make default, because during fault conditions it need to recover the traffic after the fault is cleared. The protocol itself tells that don't wait for that fault, it will go for next request. And yeah, I think even I have some test cases with QoS, because QoS is very important during this ATS and PRA enabled system performance. We need to, it's critical system performance cases, correct? So that time also how much overhead is adding with this protocol, all these things we can verify here. And yeah, functionality covers how much capability we covered inside. Yeah, the key takeaways, like just to wrap up only two lines, like this capability helps a lot in today's modern architecture, because today's modern architecture is using unified memory regions across virtualized environments and cloud environments. So that's why these capabilities help, inbuilt these capabilities has these translations and protection mechanisms. So, and verification standpoint of view, is complex to verify because we are not verifying only one capability. We have dependencies between one capability to other capability. So this verification standpoint, we need to verify for a lot of multiple pass IDs, because then only we will understand so many caches will be there in the devices, and so much overhead traffic also added during that time. So this helps like to verify all the corner cases and system level scenarios. So I think in my test benches to achieve these corner cases in system level and other environments, we use this setup for the fault injection techniques, everything, all the setups we use it, and this technique helps nicely to verify, to get these corner cases in the first phase of verification only. Yeah, any doubts you have?
So do you like do for physical like PFs and VFs as well?
Yes, sir. PF and VF also, because for PF ATS is different. For VF also we need to enable with different configurations, because it don't use the same configuration of PF capability. So different capabilities we need to enable for PF and VF. And for PRI, it is same capability. Okay, thank you.